Geometry Section 2.2, biconditionals and definitions. The reason that I have this document here, I'm sure, is because one year I had a substitute for the day of this lesson, so I typed this up, and I'm very glad to have it now. It would have been a handout if this had been a normal year, and if you would like a copy of it, I think I'll be sure to put that up with the video. If I forget to do that, somebody remind me, and when I put it up on Google Classroom, I'll put the handout as well. Probably don't need it, but if somebody wanted it to print and hole punch and put it in with your notes, you could do that. Okay. All right. So first of all, we say consider the conditional. If a number is even, then it is divisible by 2. And then they ask us to write the converse. I've already done that. This is what you should have learned to do in 2.1. If you can't write a converse yet, you shouldn't be on to this video. You should be working on your 2.1 homework. All right. It says, so I wrote that, and it's if a number is divisible by 2, then it is even. So we have a conditional and its converse. Now, are those true? If a number is even, then it's divisible by 2, meaning that if you divide it by 2, you get an integer as a result. Okay? And yes, that's true. You divide, 4 is even. You divide it by 2, you get 2. That's an integer. 2,348 is divisible by 2, and it's also an even number. Okay? The converse, if a number is divisible by 2, then it is even, is also true, because if it's divisible by 2, then it's even, meaning that it ends in 0, 2, 4, 6, or 8. And that's always the case. Okay? So we get to a new term, and it's called a biconditional. Biconditional is the combination of a conditional and its converse. Both must be true. We just verified that these two are, into one sentence. All right? Now, it continues, and it says, since the conditional and its converse in the above example are both true, they can be written as a biconditional. And here's how it works. It's a number is even if and only if it is divisible by 2. Okay? So the mechanics of this are you take either one of these. I have taken the first one, the condition that was given, and you basically take out the if from the beginning, and you replace the then with if and only if. Okay? Now I'm going to show you why this works now. Okay? First of all, notice the if part. A number is even if. Let's just pretend like this part's not here. Okay? That's gone for just a moment. Okay? Well, what would that be equivalent to? A number is even if it is divisible by 2. Well, what follows if is the being divisible by 2 part. Well, that would be like this one then. So a number is even if it is divisible by 2 is like saying the converse that I wrote above. Okay? But don't want to erase that because I think it'll take it away. So there. But if we take away the if and, the and just connects the two things. It's if and only if. So it's two things. If we took away the if and, then a number is even only if it's divisible by 2 is an equivalent saying to if a number is even, then it is divisible by 2. Okay? So together then, this if and only if statement, this biconditional, basically states that both of these things are happening, both are true. Okay? Now again, this is from a sub-year, so when I say review examples 1 and 2, you don't need to do that in your textbook because we're going to go to the presentation software right now and look at examples 1 and 2. Here's one. It says, consider this true conditional statement, write its converse. If the converse is also true, combine the statement as a biconditional. If x equals 5, then x plus 15 equals 20. We saw one very similar to this in the previous lesson. This is true because if you plug 5 in for x, the conclusion will be true. The converse, just switching the blue and the red, right? Because switching hypothesis and conclusion. If x plus 15 equals 20, then x equals 5 is also true, again, for a different reason. Here you'd have to solve by subtracting 15 from both sides, and you subtract 20 from 20 minus 15, you'll get 5. You'll get x equals 5. So both of these are true. They can then be combined into a biconditional. Let me give you a head start and see if you can do that. Use if and only if. You could write a biconditional, and it would be one of these two things. It would either be x equals 5 if and only if x plus 15 equals 20, or equivalently, you could kind of mock the second one here and say x plus 15 equals 20 if and only if x equals 5. They're both true. And there you have it. There's one of them. Again, if you flipped blue and red because they kind of imply each other, that would have been fine. How about this? Write the two statements that form the biconditional. So here they give you the biconditional, and then they want to write it separately. And basically that would be like saying this: if lines are skew, then they are non-coplanar. But because that used the term if and only if, the phrase if and only if in the middle, you could just the same say if lines, and again, identifying the lines first is good. I forgot my E on R. If lines are non-coplanar, then they are skew. And by the way, both of those are true because the biconditional is true. Lines that are skew, they are non-coplanar. Skew lines will not lie. Two lines that are skew with each other will not lie in the same plane. And if lines are non-coplanar, then they would be skew. Yep. Okay. And we're back here. We can use arrows to show conditionals and biconditionals. And I worry about the amount of vocabulary, but you just got to get used to that. I talked about it in class. This is the nature of geometry. You got to sink yourself into it and understand vocabulary. It's a lot less computation in geometry, and it's a lot more verbiage, especially at the first of the year. Okay, so embrace it. Don't hide from it. You can't. All right. So here's the thing. A conditional, like if A then B, whatever A is, whatever B is, it's just standing in there for hypothesis and conclusion, can be written with an arrow, A arrow B, okay? And then the converse of this statement would be B arrow A. The arrow is the word implies. That's what this says down here, okay? The arrow signifies that it's the word implies. Think about it this way. Again, we use the example that I used in the previous lesson. If the weather is fair, then Mr. G's class takes a mask break. If the weather is fair, then Mr. G's class takes a mask break. I could replace if and then. I could take if and then out of that statement, and I could say the weather is fair implies Mr. G's class will take a mask break. Okay, that's the same thing. So for the arrow notation, it's kind of convenient that we use the word implies. This literally says A implies B. This says B implies A. Now, if they're both true, as we're establishing in this lesson, the biconditional that combines these two would just be A and B pointing at each other. And quite frankly, again, the equivalent to this, an equivalent statement could be this, right? Because they're both implying each other. It doesn't have to be A then B. It can be B then A if the arrows are pointing in two directions. Okay? And that's kind of what this says right here. Now let's talk about good definitions. We're almost done. Good definitions, we've already encountered good definitions in the geometry book. I'm not going to go through it again, but I'm thinking of the definition for adjacent angles. And in my video where we covered adjacent angles in chapter 1, I talked about, that it's a very good definition that they have to share a vertex, they have to share a ray. What do I say? Share a side, I guess is what they say, and share no interior points, no common interior points. And I go with kind of each one in that video why excluding one of those parts would make it not a good definition. So definitions are very important to us, and I will make the bold claim that every definition in our geometry book from section 1.1 to section 12.6 and everything in between is a good definition because they follow these rules. Rule number 1 is it uses terms that are either defined or commonly understood. Okay, so things that we already have a definition for, or things that are plain speak. 2, they are precise, meaning they avoid avoid words like large or almost. Okay, large is a relative term. Like you could see a large insect, but it's not as large as a football field. So what's large? It depends on what you're comparing it to. Almost is a bad word to use in a definition because who knows what almost is. The reason that the good definitions are here in section 2.2 is because it also needs to be reversible, which is to say that it is a true biconditional. Let's take a look. Just two more examples. To show that this definition of triangle is reversible, then write it as a true biconditional. A triangle is a polygon with exactly 3 sides. A triangle is a polygon with exactly 3 sides. The question is, can you write that as a biconditional? A polygon with exactly 3 sides is a triangle, right? So that's reversible right there. And this would be long to write, and I want to make the video short, so I'm just going to roll to their answer, make sure you agree. There's a conditional. If a polygon is a triangle, then it has exactly 3 sides. The converse would just flip red and blue here. If a polygon has exactly 3 sides, then it's a triangle. Pause the video if you need to convince yourself that both of those things are true. And then we could combine them in a biconditional, like so. Okay? And then one more. Is the following statement a good definition? Explain. An apple is a fruit that contains seeds. An apple is a fruit that contains seeds. Is that a good definition? Most of the time when I go through this with a class, the first volunteer will say, well, no, because strawberry is a fruit that contains seeds, and a banana is a fruit that contains seeds. While an apple is a fruit that contains seeds is a true statement, it's not good enough, right? And they'll come up with other fruit to be the counter example. But really, in a geometry sense, and again, I know it's about language, but in a geometry sense, it's the problem here is that it's not reversible. A fruit that contains seeds is an apple. If a fruit let's make it an if-then statement. If a fruit contains seeds, then it is an apple, is a false statement, okay? So this is not a good definition, okay? That is all. Thanks for watching.